Um, Today we are presenting our system for temperature and evapotranspiration monitoring, STEM for short. And some of the reasons you might want a sophisticated agricultural monitoring system involve, most importantly, is resource conservation. You're able to detect pooling of water in subterraneous soil, and if there's an unnecessary amount of pooling, then you can adjust accordingly. You can also gain a lot of data about the soil you're using and which potting material would be optimal for your crop. It also helps farmers and vintners produce not only a higher yield, but also a more quality yield. In the case of a vintner, you can control the sugar content of grapes if you know how much water, or you can control directly the sugar content of grapes through the amount of water it receives. And if you have the knowledge of that, you can actually produce wine exactly how you want in a controlled environment. Our system will be rugged, easy to use, and affordable. More so than current systems are today. Our system is also unique in that it combines two sensors for monitoring evapotranspiration and also soil moisture. That will give us a good snapshot of the water content of the leaves above the soil, the leaves in, say, the vines, and also give us a soil moisture profile of the soil. Obviously. It will also give us a continuous monitoring of soil moisture levels and evapotranspiration rates. And the big thing about it, of our system, is the wireless communication. With that, it's pretty much a install and forget system, or we're hoping it will be, where you just leave it in the ground and it pushes data wirelessly to a database.
So our main sensor here is the soil moisture sensor, and what it does, it calculates the volume of water content. Ostensibly, this is the amount of water that's contained within the soil sample. In our case, we are going with the Vigitronic sensor, and this uses transmission line techniques to measure the volumetric water content. This has relatively low power consumption throughout the cycle.
So the other sensor we have is MLX IR sensor. We're all aware of what IR sensor does. We'll be using it to measure the temperature of the leaf, since the leaf's temperature changes because of humidity or whatever evaporation they have.
Our power system, this device is going to be powered off the battery, and more importantly, this device would be able to be recharged through solar panels attached to each other.
So here's our 3D rendering of our alpha prototype. The main components are this audio jack right here. So that is designed to take in the input and also provide the power for the sensor that we have, which we've chosen to be the Vigitronics. So in our demonstration upstairs, we have an audio jack connection with that sensor. Over here is our boost circuitry, PSOC 4100. We also have a very similar battery charging system with a barrel jack connector. This is where the solar power would come into, and so then that way that provides power if the battery needs to be powered up and recharged. That's the JST connector for the battery. Additionally, for prototyping purposes, we have connectors here for the MLX IR sensor.
And we have a video demonstration of our prototype upstairs.
How about just open it up in YouTube? Just put that
Click the,
YouTube.
yeah.
This is our outboard, and right now we have it connected to our solar panel right over here. This provides a very steady voltage that goes in and charges up our battery, located right over here. It is transmitting information through the XP, and right now we only have one sensor hooked up, and that would be the soil moisture sensor. Right now we have it stuck within the dry dirt, and as I take this soil moisture sensor out, place it inside the Hero Dirt, and this information will be transferred over to XP for finally placing it in the BC Special.
This is the dry dirt. That spike down was from when he pulled it out, and now it's in the Hero Dirt, where you can see it spike up because it's a little bit more moist. Now he's gonna pull it out and put it into the wet, and you'll see it spike down and spike up to the highest point. There's the XB. That's hooked up over there to the test setup with Jeff.
Did you guys make this last night?
About an hour ago.
Same clothes.
I haven't changed in a while.
Maybe double click on it.
So this is a demonstration of the system.
Yeah, so this is the current state of our Alexa sensor.
That looks more like a rap video.
You can see in the background is the Walkman Alex monitoring, and you can see it tracking my movements. It's kind of a lag, but it's pretty slow.
The sensor itself is back here.
So this is our power system. As I mentioned, there is a battery charger circuit. Here we have two sources of power that can apply. Either a 6 volt DC voltage that's inspired through a solar panel or a wall outlet, and a much smaller 5.1 volts that is connected to a USB charger. This battery charger goes out into our battery, which is set at 3.7 volts, and provides a series of stats and LEDs so we can check upon these charge data at any time. Our regulator system is very simple. We have a total of 2 voltage lines that we need to take care of, a 12 volt line providing 650 milliamps of power, and a 3.3 volt line. The only sensor that consumes the 12 volt line is the soil sensor. Everything else on our board consumes the 3.3 volt line.
So our digital system actually has been greatly simplified this week since we've pretty much decided to go with the Vegetronics. What we had up here was a decagon block, so what that would have been a UART block using what's called a DDI-12 interface, which is kind of a proprietary interface that the decagon company provides. And so that part is actually going to be gone now since we're going to go to Vegetronics. So all that leaves us with is a UART block for the XB, which is doing simple transmit and receiving, and then the MLX sensor runs off with an I2C interface. So now we actually have to focus a little bit more on the analog side of our project and of the PSOC. So the Vegetronics outputs a 0 to 3 volt DC signal proportional to the volumetric water content, and there's a certain amount of error that we have to be within, and a big consideration that we have to take into account is noise, whether that'll bump us out of the margin of error that's acceptable. We have to take into account crosstalk and other environmental factors that will provide noise on our lines. So right now, in the current test setup that we have, we're using a single-ended SAR ADC. The only reason we're using the SAR is because that's the only one available right now in the current PSOC that we're using. It's a pretty simple ADC conversion, so type of ADC probably doesn't matter too much. We have talked some about using a differential signal because that provides greater noise immunity. So in that case, we would obviously switch to a differential mode ADC. So all these things have to be discussed and figured out, and those details will be sorted out later, and then I'll decide what ADC we ultimately use.
That's our camera we're using.
Sorry, Ed, just keep going. Yeah.
As you mentioned before, these 3.3 volts is power and communicates your ITC port.
Alright, so as we mentioned before, we recently decided to switch over to the Vegetronics sensor. This was a decision that's taken us a long time to make, and it has been most recently cemented in the fact that we're running a soil test, actually as we speak, in the Robert Mondavi Institute. We have 2 samples of soil that are in an oven right now, being heated up and monitored by Jean-Jacques and myself. Basically, we're recording both the Decagon data and the Vegetronics data and working it against the data logger that they currently have. To do further tests, because we're eventually going to have between 3 and 6 of these things in the ground. I also went and dug a big hole in the vineyard with Jean-Jacques yesterday morning. So we have a large hole that we can actually stand in and get down to 4.5 feet or so underground. That's how we'll be able to test the noise with the multiple sensors. Also, there's some questions as to the ruggedness of this sensor. It's not as tested and used in industry as the Decagon is, so we will be having to make some considerations for that and waterproofing it and stuff. The other sensor that we considered was the Decagon. This one is what is currently used by just about everybody. It's really nice. It has soil moisture as well as temperature all built in. It uses SDI-12 interface, or you can put it in DDI mode, which is how we were reading it. It's not as good as you can see in the next slide, which shows the specs. Basically, as long as the Vegetronics is able to keep par with that, the Vegetronics is better in every single way. It consumes less power, it has a greater operating range, although I don't think we're going to be getting to 85 degrees Celsius, and it's around a quarter of the cost. So all of these factors combined, since so far the Vegetronics has been performing on par with the Decagon, we will be moving forward with the Vegetronics.
Alright, so with our new beta revision, we decided to go to PSOC 5. Part of the reason we went to PSOC 5 is at that time we were still considering Decagon. So I wired some of the things to accommodate both either a Decagon or a Vegetronics sensor, depending on the setup, so it would be versatile that way. We'll be using 5 volts instead of 12. We basically had a legacy 12 volt line from an earlier revision, so we're dropping that voltage down. We'll then be able to have multiple sensors, so then that way we can test multiplexing and reading, have a more realistic setup of what we have in the field instead of just reading one. Off-chip switching will basically be just switching these sensors on and off as needed using MOSFETs, and so that way they're not always on. And then we also decided to put the XP straight on and try to put as many things onto the board, so then that way you have less air wires and so forth when you're testing.
Good. So we gotta move on.
Oh.
So.
Good timing.